Chapter 4 Axial Loading Part A. We do know that stress is normal force over an area if we call it equation 1, and at the same time we do know a strain is a change in length over the original length if we call the dx the length of our element within the whole shape, and we call it equation 2. From Hooke's law we do know that there is a linear relation between stress and strain, and that's nothing but stress is equal to modulus of elasticity times strain, and that's equation, the third equation. And if we combine all these three together, we can say stress is equal to modulus of elasticity times a strain. And if we arrange the equation based on d delta, we can get d delta is equal to uh, n times L over EA, which dx stands for the length of our elements. Mhm. In studying of delta deformation, we can have two scenarios. Scenario one is when we do have a discrete parts, which completely separated parts of a which consist of different blocks. For example, if we call it uh, block A fit in relation with block 2, block blah 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 to the last one, and happen to handle the different or a various axial loads like P1, P2 to P4. In such case, we can have our delta like a summation of n times L over EA. So that's, if it's two part, that's N1 L1 over E1 A1 plus N2 L2 over E2 A2. And the second condition is when we have a continuous shape like what you can see here. In that case, we do need to go for integration from 0 to L for the whole length of our structure, and that's in numerator is nx times dx over ex times ax. Let's put it to an example to see how it goes. So in this example, you can see a 36 A36 steel bar with a diameter of 50 millimeters, subjected to loading, which you can see here. Determine the displacement at the far end D, which and also the displacement of the, the points in the midsections. So by observing the steel rod, we can easily see this is the scenario one. This is this discrete part. It just comes to, if we call it, from C to D part one, from B to C part two, and from A to B part three. These are separated blocks which just added up together. And in that case, we just need to go by summation of forces. So in such case, delta is a summation of NL over EA, and just in case, for A36 steel bar, from the table of the material properties, uh, modulus of elasticity for steel stands is equal to 200 gigapascal. That goes by 10 to 9 Pascal. And area for a such bar with 50 millimeters, it's pi times 0.025 squared meter squared. Let's look at the problem and approach the problem from point D, from right to left. So if you look at the structure from right to the left, you can easily see as you move from D to C, you are experiencing only 70k push until you reach to the trajectory point of these 40 kilonewtons in the other direction. So as if we just take as if we can just take from C to T, C to D out and call it piece one. One can say I can have my first piece in a push at the both side by the amount of 70 kilonewtons. And in that case, delta 1 is nothing but a negative for a push, 70 times 10 cube newtons times the length NL over EA for the first piece. So this is our area, pi times the pi times 0.025 square meter square times that's our A, and this is our modulus of elasticity. So that's N1 L1 times A1 E1. Because cross section cross sectional area does not change for hole shape, and materials is a homogeneous A36 steel, we can just go by A and E for all deltas, but the change are in uh, axial force and the length. Mhm. And in that case, it's going to be a negative 0.26 in terms of millimeters. Likewise, if we observe the second part, as soon as we reach to C, there is a contradicting force of 40, which contradict this 70 push. So the superposition gives me a steel 30 push because 70 is higher than that. And as I'm traveling from C to B until I'm reaching to the trajectory starting point of this 80 kN, I'm not experiencing any other force but 30 kilonewton, as if I can take part 2 out and say this is another push at both sides, 30 kN at both sides for BC in the length of 1 meter. And delta 2 is again a push, 30 kilonewton times length of N2 times L2 over A2, which is A and E. And if you do so, that gives you a negative 0.076 millimeters. I continued for a more exact values, but just in case. And likewise, if we just observe the last piece, which it just shows us, so up to here we had a 70, from B to C we had a push of 30. And all of a sudden, as soon as we enter to the third territory, we can experience a 80 in a positive 80 kilonewton in positive x direction. So we had a 30 push, 80 pull. It gives us a as if part A to B experiencing a 50 kilonewton pull at both end. Mhm. And if this time we just go for a positive, because this is a tensile member A to B, and that's nothing but N3 L3 over EA. And if you do so, that gives you 0.255 millimeters for the third part. And due to uh, superposition, you can add them up all together for first plus. Now, if due to delta is summation of NL over EA, if I just simply add them up together, I will have their deformation. I can have my answer for the whole structure. So delta D is delta total. Delta at D is the at the free end is total delta, which consists of delta 1 plus delta 2 plus delta 3. If you add the previous values together, it gives you a negative of 89 to 10, negative 3 millimeters, and the negative sign says that D moves to the left, so it just comes a bit to a bit closer to A.